Right, this video is just to quickly go through how the graph of cos, graph of sine, and graph of tan are derived and where they originate from, and also to make sure you understand what those graphs look like, because before you go on to solving trigonometric equations, you need to know those shapes of those curves. So first of all, I'm going to start off with y equals cos x. So the graph is, as you can see, is on the bottom diagram. It's generated by looking at the unit circle. So if we imagine a circle where from O to B is 1 unit, okay, length 1, then cos of an angle here, it's 45 at the moment, is defined as the distance that we project straight down onto the x-axis. So if you imagine a vertical projection straight down onto the x-axis, that distance measured there gives you the size of cos of that angle. So that is what we plot on the against y. So if we go back to roughly where alpha is 0, or practically 0, see if we can get it there. So you can see we're projecting pretty much 1 here, and that's where it starts at the top here. And as we move round, take it round, we go through to 90, then we get to 0, because the projection down onto here is practically 0, this angle I'm at. Then as I get to 180, it's going to be -1, because we're in the minus axes, so it projects down to -1, and then we're going to go round to 270 and round to 360. Now with this program, it's not possible to show the continuation of the graph, but if you can imagine, the second time you go round, you're just going to repeat the cos curve because the projection is going to be the same. So as we can see, this point here will be the same as this point here. And if we go backwards, so if you can imagine this point and going backwards, it's just repeating going backwards here. So you can imagine negative angles being backward, starting the origin going backwards. So the cos curve goes on forever, both negative and both positive, and it just repeats itself over and over again. And it's important you know that it's a maximum at 0, that it's 0 at 90, that it's a minimum at 180, 0 at 270, and maximum at 360. Make sure you draw a copy of these graphs and you have them and you know them. And you need to also know that 90 is pi by 2, 180 is pi, 270 is 3 pi by 2, and 360 is at 2 pi. If we look at the sine curve, we can see it's just like the cos curve. Let's just get rid of the cos curve for now. It's the projection onto the axes. So therefore, we're projecting vertically, well, horizontally in this case, but it's going to be out of sync because where cos projects onto the x-axis is large, obviously on the sine projecting onto the vertical axis will be small. And when you get around to here, you're going to flip around. So sine starts off at 0, moves round to 1 at 90, moves round to 0, projecting down onto the y-axis on this one, and gives you a value of 0 at 180. As we move around, 270 is -1, 360 is 0 again. And again, you can imagine it repeating. This angle here is going to be the same as this angle here. And this value here is going to be the same as this value here. That's also quite important to note. So there's the sine curve. Now tan's there's lots of interesting ways to project tan. You could even draw a tangent and measure where it projects. I'm just going to actually look at where the point projects onto this vertical line that goes through to point 1. That distance there actually gives me also the tan of the angle. So if I'm going a line that goes through the origin and B and projects onto that line, this distance up here will give me the tan. And you can see, therefore, it actually goes beyond 1. And actually, as you get close to 90, obviously, they're going to get parallel lines, and effectively, it's going to become undefined at 90. It's not going to project at all. And then as we go round to here, notice I was talking about the line between B and the origin projecting onto here. Let's just bring it around so we can see it projecting. It will project down to the below the x-axis, so we make that the negative value of tan. Keep going round. We get to 0 at 180, and then beyond 180 we start getting bigger again, and eventually at 270 again will be undefined at 270, and then we project here and we come up on the bottom here, and again this graph will repeat itself. Okay, it goes on forever. but you need to know that it's 0 at 0, undefined at 90, 0 at 180, undefined at 270, 0 at 360, and it follows this pattern. You need to know that off by heart. And of course, 90 is pi by 2, 180 is pi, 270 is 3 pi over 2, and 360 is 2 pi. All right, that's the curves. And when we want to solve equations, so say we want to solve an equation where tan alpha equals 0.52, you look at 0.52 in the y-axis, we get our first value from our calculator here, which is 27.4. Then what you need to realize is 180 to that point, this curve is exactly the same as this part of the curve. So you just add on 27.4 to 180 to get this value here, which will be 207.4. And similarly, you can get the next value here, and so on, and so on, and so on. Let's go back to cos and look at just solve an equation of cos. So we want to find out where cos of our angle equals about, let's look at it. Let's see where cos of our angle equals 0.8, for example. Let's just move it around a bit more. There we go, we're equaling 0.8. We get a first value from the calculator, which will come out as 37.2. Then you look across the graph and you realize that this part of the graph, or this part of the graph even, so from 360 back, is the same shape as this part of the graph here. The cos curve is symmetrical, the sine curve is symmetrical, and tan, they all has translational symmetry. On this one, this shape of the curve is symmetrical. So this distance here is 37.27, and this distance here is also 32.7. And therefore, you take that away from 360, because we know that maximum comes at 360, to get ourselves the lower value. Anyway, I'll show some examples with that in the next video.